That is today's T distribution. There are many T distributions, each with its degree of freedom, which is the only parameter of this distribution. At T distribution is similar to the standard normal distribution as shown in the figure. It is flatter and wide, thus having long points. As we can see that is today's the diagram distribution. Number 3, there are many T distributions. Is related with its degree T distribution, without which is the only parameter as we are distributing degrees of freedom. At T, the graph is becoming steeper and is coming up, as you can see with the dotted line. As and when standard normal distribution or T distributions is with infinite number of degree of freedom, it is becoming more steeper at the top. That means it's behaving like a normal distribution. As the degree of freedom increases, the T distribution comes closer to the standard normal distribution. And when the degree of freedom becomes infinitely large, so it becomes the T distribution and the Z distribution becomes indistinguishable. How this T distribution is used practically? It is x bar minus mu upon s divided by under root n, and that would have n minus 1 degree of freedom. It is therefore possible to know the sampling distribution of x even when sigma is not known. This result is really useful when the sample size is not very large. As we have seen earlier, if the sample size is large, the T distribution with large degree of freedom can be approximated by the Z distribution. The t distribution is used when the degrees of freedom are not larger than 30. And if the degree of freedoms are larger than 30, t distribution is approximated by the standard normal or the z distribution. If n is significantly large, so we can say that probability p dash is similar to p comma p into pq upon n, because q is 1 minus p. This approximation works quite well if n is sufficiently large so that both np and nq are at least as large as 5. Now, interval estimation. Suppose we want to estimate the mean income of a population of households residing in a part of a city. We might proceed by picking up a random sample of 100 households from the population and calculate the sample mean. That is the mean income of 100 sample households. If the absence of any information, the sample mean can be used as a point estimate of the population mean. The lower the standard error of the mean, the greater is the confidence or the correctness of our estimation. This process is further refined in interval estimation, wherein we present our estimate as an interval and quantify our confidence so that the true population parameter is contained by the estimated interval. Now, what is confidence interval? The probability that the interval estimate will contain the true value of the population parameter that is being estimated. If we say that a 95% confidence interval for the population mean is obtained by spanning 1.96 times the standard error of the mean on either side of the sample mean, we mean that if we take a large sample of size n, say 1000, and obtain the interval estimate from each of these 1000 samples, and then 95% of these interval estimates would contain the true population mean. Confidence interval for the population mean. Suppose it is known that the weight of cement is packed bags is normally distributed with a standard deviation of 0.2 kg. A sample of 25 bags is picked up random, and the mean weight of these 25 bags is only 49.7. We want to find a 90% confidence interval for the mean weight of cement in filled bags. This is a practical problem. We will see how we calculate all these values. If X is distributed normally with a standard deviation of 0.2 kg, then the standard error will be sigma x bar equal to sigma upon under root n. That will be 0.2 divided by under root of 25, which comes out to be 0.04 kg. Now, to estimate the confidence interval, since n is less than 30, we will use t distribution. And for t distribution, we have the formula t equal to x bar minus mu upon sigma upon under root n. When we are going to put up the values, we are going to get a mu, because mu is unknown, we know the t, mu is unknown. For calculating mu, we will be getting 49.7 plus minus 1.65 into 0.04, which comes out to be 49.63 and 49.76. Now the question arises, how we got this plus minus sign? Plus minus sign is basically for under root 25. So here we can see graphically how this is being depicted. And this information is for 90% confidence. As a matter of practice, statisticians usually consider samples of size 30 or more to be large. In the large sample case, a 95% confidence interval estimate for the population is used and is given by x bar plus minus 1.96 times sigma upon under root n. Now we have to calculate the sample size for estimating population mean. We assume that the population distribution is normal and the population standard deviation is known. In such a case, the sample size required for a given confidence level and a required accuracy can be easily determined. Suppose we know that the weight of cement in field bags is distributed normally with a standard deviation of 0.2 kg. We want to know how large a sample should be taken so that the mean weight of cement in a field bag can be estimated within plus or minus 0.05 kg of the true value with a confidence level of 90%. For that, we can use the formula x bar plus minus 1.645 times sigma upon under root n, which contains the true value of the population mean of 90% of the time. We also want the interval x minus 0.05 and x plus 0.05, which will give us a 90% confidence level. Therefore, transforming the values into the formula, we get n equal to 43.3. This is obtained after calculation. So we must have a sample size of at least 44 so that the mean weight of the cement in a field bag can be estimated within plus or minus 0.05 kg of the true value with 90% of confidence. Now we move on to Unit 11, that is related to testing of hypothesis. First of all, we will see what is meant by hypothesis and what are the procedures which are applied to test these hypotheses. Study a class of problem where the decisions made by a decision maker depends primarily on the strength of the evidence thrown up by a random sample drawn from a population. To test a hypothesis, a statistical procedure is followed, and this procedure is called testing of hypothesis. Hypothesis, or more specifically a statistical hypothesis, is some statement about a population parameter or about a population distribution. If the population is large, the hypothesis is tested on the basis of the outcome of random sampling. A hypothesis is a statement about a population parameter or about a population distribution. In any testing of hypothesis problem, we are faced with a pair of hypotheses, such that one and only one of them is always true. One of this pair is called the null hypothesis and the other one is called the alternative hypothesis. The null hypothesis is represented by H0 and the alternative hypothesis is represented by H1. Now, what is meant by null hypothesis? A null hypothesis is called by this name because in many situations, acceptance of this hypothesis would lead to null action. Rejecting the null hypothesis leads to a change in status quo. If the population mean is represented by, we can set up our hypothesis as H0 is to mu is equal to 20, and the alternative can be shown by H1 is to mu greater than 20. What we have represented symbolically above can be interpreted to mean that the null hypothesis is that the mean population is not greater than 20, whereas the alternative hypothesis is that the population mean is greater than 20. It is clear that both H0 and H1 cannot be true, and also that one of them will always be true. At the end of our testing procedure, we will come to the conclusion that H0 should be rejected. This also amounts to saying that H1 should be accepted and vice versa. There are two types of error when we are calculating or when we are studying hypothesis. That is type 1 error and type 2 error. If we wrongly reject H0, when in reality H0 is true, this error is of type 1 error. And similarly, when we wrongly accept H0, when H0 is false, the error is called type 2 error. So in the diagram here, we can see that if H0 is true, accept H0. And we're rejecting H0, that is type 1 error. And if H naught is false and we are accepting H naught, that means it is of type 2 error. Let us take a situation where a patient suffering from high fever reaches to a doctor. And suppose the doctor formulates the null hypothesis and alternate hypothesis as H naught, the patient is a malaria patient. And H1 is the patient is not a malaria patient. Then how doctor will study and how he will proceed. Suppose in case 1, the null hypothesis H naught is really true. That is, patient actually a malaria patient, and after observation, pathological and clinical examination, the doctor rejects H naught. That is, he or she declares him or her a non-malaria patient. It is not a correct decision, and he or she commits an error in decision known as type 1 error. In case 2, suppose that the hypothesis H naught is actually false. That is, patient actually a non-malaria patient, and after observation, the doctor rejects H naught. That is, he or she declares him or her a non-malaria patient. It is a correct decision. Case 3 is, suppose that hypothesis H naught is really true. That is, the patient actually a malaria patient, and after observation, the doctor does not reject H naught. That is, he or she declares him or her a malaria patient. It is a correct decision. The fourth one is, suppose that H naught is actually false. That is, patient actually a non-malaria patient, and after observation, the doctor does not reject H naught. That he or she declares him or her a malaria patient. It is not a correct decision, and we can say that he or she has committed an error in decision known as type 2 error. Both these errors are bad and should be reduced to minimum. For a given sample size, these two errors neutralizes each other. If the testing procedure is designed as to reduce the probability of occurrence of type 1 error, simultaneously the probability of type 2 error would go up and vice versa. What can best be achieved is a reasonable balance between these two errors. Type 1 error is much more severe than type 2 error and so needs to be controlled. Type 1 error generally results in a financial loss to the company, whereas type 2 error generally results to an opportunity loss for a company. Now we move on to the significance level. Probability of type 1 error needs to be controlled. This is done through specifying a significance level at which the test is conducted. The significance level, therefore, sets a limit to the probability of type 1 error, and test procedures are designed so as to get the lowest probability of type 2 error subject to the significance level. The probability of type 1 error is usually represented by the symbol alpha, and probability of type 2 error is represented by beta. Testing of hypothesis suffers from the limitation that the financial or the economic cost of the consequences are not considered explicitly. In practice, the significance level is supposed to be arrived at after considering the cost of consequences. It is very difficult to specify the ideal value of alpha. Probability of type 1 error should be low. That is, the value of alpha should be lower. In practice, most tests are conducted at alpha equal to 0.01, alpha equal to 0.05, or alpha equal to 1 by convention as well as by the experience. We take up examples. Testing of chemical. If wrong inferences, whole group of users will be poisoned. Prefer high significance level, that is high probability of type 1 error, and reject H naught when it is not true. Reassembling a big machine. If wrong inferences are drawn, some parts may be repaired or replaced. Prefer low significance level over here. That is high probability of type 2 error. That is accept H not even it is false. What is the effectiveness of a drug? H naught, it had no effect, and H1, it had effect. So graphically, we can see that where we stand and where what is the at what level we can accept H naught and reject H1. This is a 5 level of significance. Accept means at 5% level of significance, data does not allow us to reject a null hypothesis. What is the p-value of a test? The significance level is arbitrarily fixed. A better way of expressing the conclusion of test is to state the p-value or the probability value of the test. The p-value of a test expresses the probability of observing a sample statistic as extreme as the one observed if the null hypothesis is true. What are the hypothesis testing procedures? There are basically two phases in testing a hypothesis. In the first phase, we design the test and set up the condition under which we shall reject the null hypothesis. And in the second phase, we use the test based on the sample evidence and draw our conclusion as to whether the null hypothesis can be rejected or else what is the p-value of the test. Specifically, these are the steps. What is the procedure? Step 1, state the null and the alternate hypothesis, that is state H0, H0 and H1. Choose the test statistics, that is the sample statistic that will define the critical region. Specify a level of significance of alpha. Define the critical region in terms of the test statistic. Compare the observed value of the test statistics with the cutoff value or the critical value and then decide to accept or reject the null hypothesis. But these are the 5 steps which are performed. What is needed? Inspections sometimes do not allow inferences. For example, a manager comment that the average work efficiency is 90%. And suppose our calculation gives the result 90%, 95% we accept, 40% we reject, and 89% we have to apply some thought. So intuition does not work. So one has to decide on the basis of sample information. Testing the population mean. Under different conditions, the test procedure have to be developed differently. There are many cases like when the population variance is known or unknown, when the distribution of sample mean set can be approximated by a normal distribution, and when test is two-tailed test or one-tailed test. So that means depending upon the conditions given the problem, we have to change our assumptions. Now, under what condition we have to apply which distribution? It is either we can use normal distribution or we can use t distribution. When the sample size is larger than 30 and sample population SD is known, we apply Z test. Similarly, if the sample size is larger than 30 and when population SD is not known, again in that case we apply Z. But when sample size is larger than 30 and population SD is known, we apply Z. And in the fourth case, when SD is population SD is not known, then in that case we apply T test. There are examples which depicts how we can apply and what how we can start with the testing of hypothesis. Suppose we take up an example of bulb manufacturer. Reject if the life is short, that means it is of bad quality. Reject if life is very high, that is large production cost. In that case, we can say that H0 is to mu is equal to mu H0. This is the null hypothesis, and the alternate hypothesis is H0 is to mu is not equal to mu h naught. And similarly, if we move on to another example of bulk wholesaler, he rejects if the life is shorter, that is of bad quality, and except otherwise, who is bothered about the cost? The parameter is not considered of cost, then in that case, h naught is to mu is equal to mu h naught, and your alternate hypothesis is h naught is to mu is greater than mu h naught, and graphically it is shown below. Now we take up an example. Basically understand how all these things what we have discussed are applied practically in a code. Suppose for RM manufacturer, here the problem is what are the conditions given to us? We are going to test the mean when SG is known, and that means standard deviation is given to us in the problem. The condition must withstand 80,000 kg per square inch of the load, and your standard deviation is 4,000 kg per square inch, and mean is 79,600 kg per square inch. N is 100. H naught is to mu is equal to 80,000. That means H naught. And H1 is to mu is not equal to 80,000. Alpha is 0.05. Standard error of mean is calculated, that is sigma by under root n. Putting up the values, we get 4. Then we calculate Z value, and that is equal to x bar minus mu h naught upon sigma divided by under root n. Now, if Z calculated value is less than tabulated Z value, it is accepted. And if Z calculated value is greater than Z tabular value, we will reject the condition. This is how the problem is solved. Now, how to test for the proportions? For example, testing the promotability of employees. H naught roughly 80% are promotable, and committee finds that only 70% are promotable. So in that case, N is 150. Probability PH naught is 0.8. QH naught, that is 0.2. Probability will be 0.7, and Q will be 0.3, and alpha value is 0.05. So we will be calculating the standard error of mean for the probability. In that case, we use under root PQ upon N, and we get up the value as 0.0327. Now, we move on to Z calculated value. For Z calculated value, we have to find P bar minus BH naught upon sigma P bar. If Z calculated value is less than Z tabulated value, we accept it. And if Z calculated value is greater than Z tabulated value, we reject it. Now, we are testing mean when SG is not known. Example, testing of recurrent scores. H naught, it is going fine. The average score of the reduced will be around 90%. That means we can say that H naught is to mu is equal to 90. And mu H naught will be 90. N is 20. X bar is 84. S is 11. And alpha is 0.10. All these values are given in the problem. Standard error of the mean has to be calculated, but sigma is not known. We replace sigma by S. That means now it will be T calculated value is equal to x bar minus mu h naught upon S divided by under root n. Similarly, if T calculated value is less than T tabulated value, we accept the hypothesis, and if T calculated value is greater than T tabulated value, we reject the hypothesis. Now, we move on to unit 12, that is related to G-square test. If required, the equality of variances should be tested. We can also test if the population distribution is really normal. We can test whether the population distribution is Poisson, exponential, or any other known distribution. Here we can also test if two samples are independent. We can see that In G-square test, the basic criteria is degree of freedom. If we talk about 1 degree of freedom, we can see a graph which is similar to graph number 1. And if degrees of freedom are increased from 1 to 5, it becomes somewhat like the graph which is shown in the center. And if degree of freedoms are increased to 10, we can see that it is shifting like a bell-shaped curve. What are the properties of chi-square? If x is a random variable having a standard normal distribution, then chi-square will have chi-square distribution with 1 degree of freedom. If y1 and y2 are independent random variables having chi-square distribution with v1 and v2 degree of freedom respectively, then y1 plus y2 will have a chi-square distribution with v1 plus v2 degree of freedom. That means both degree of freedom will be added up. And if we have to calculate chi-square test with n minus 1 degree of freedom, then we have to calculate n minus 1 s square upon sigma square. Now we take up an practical example to understand what was stated earlier. Suppose a TV channel program manager wants to know whether there are any significant differences among male and female viewers between the type of programs they watch. A survey conducted for the purpose gives the following result. We have to calculate X square statistic and determine whether the type of TV program is independent of the viewer sex. And we take 0.10 significance level. Now, how this information given in the problem is transformed into the solution? First of all, we have to check the hypothesis. Suppose H naught, the viewer's sex is independent of the type of TV program. That is, there is no association among the male and female viewers. And H1, the viewer's sex is not independent of the type of TV program. In the problem, we are given with the observed frequencies and expected frequencies are calculated as it is row total into column total divided by the total. Now we will see how it is calculated. Here we see that news channel, for news it is 40 into 50 divided by 100, which is equal to 20. And for female it is 40 into 50 divided by 100, which is 20. And we sum up, it comes out to be 40. Similarly, for the serials, 60 into 50 divided by 100 is equal to 30. And 60 into 50 divided by 100, it is again 30, which is a total of 60. When we are totaling up column wise, it is 100, and we are totaling up across the row, we are getting 100. Now, we arrange the data on observed and expected frequencies and calculate chi-square. The following table is calculated accordingly. For row 1, observed frequency was 30, expected frequency was 20. For row 2, it was 20 and 30. 1, 2, it is 10 and 20, and for 2, it is 40 and 30. After this, our next step is to calculate OI minus EI. Values are calculated. After that, OI minus EI whole square, and the last one is OI minus EI whole square divided by EI. When we are adding up, we are getting chi-square equal to 16.66. Since we have to by two contingency tables, the degree of freedom will be R minus into C minus 1 is equal to 2 minus 1 upon into 2 minus 1, which comes out to be 1. At 1 degree of freedom and at 0.10 significance level, the tabulated value is 2.706. Now, since the calculated chi-square is 16.66, is greater than the tabular value of chi-square, which is 2.706, we reject the null hypothesis and conclude that the type of TV program is dependent on viewers. It should therefore be noted that the value of chi square is greater than the tabular value of chi square. The differences between the theory and observation is significant. What is testing the goodness of fit? A chi square goodness of fit test is a statistical hypothesis test used to determine whether a variable is likely to come from a specified distribution or not. It is often used to evaluate whether sample data is representative of the full population. The goodness of fit is typically used to determine if data fits a particular distribution. The test of independence makes use of a contingency table to determine the independence of the two factors. The two are sometimes confused, but they are quite different. The chi-square test for the independence compares two sets of data to see if there is a relationship. The chi-square goodness of fit is to fit one categorical variable to a distribution. Suppose we want to test if a worker is equally prone to producing defective components throughout an 8-hour shift or not. We break the shift into 4 2-hour slots and count the number of defective components produced in each of these slots. At the end of 1 week, we find that the worker has produced 50 components with the following break. Using a significance level of 0.05, is it reasonable to assume that the probability to produce a defective component is equal in each of the 4-hour slots? Now, if we represent the probability that the defective component comes from the ith slot by Pi, then the null and the alternative hypothesis are x naught equal to P1 is equal to P2 is equal to P3 is equal to P4, which is 0.25. And alternatives H1 is to P1, comma P2, P3 are not equal. Now, we will be shifting the given problem into a chi-square formulation table. Observed frequencies are given, and similarly, expected frequencies are calculated. And OI minus EI is calculated, OI minus EI square is calculated, and last OI minus EI whole square divided by EI is calculated. Now we find that G square comes out to be 3.28. In the above table, the expected frequency E can be calculated as NPI, where N, the total frequency is 50, and each PI is 0.25 under the null hypothesis. And we have K equal to 4, that means degree of freedom will be 3, and the significance level is 0.05. The cutoff value of the chi-square statistic should be 7.815. Therefore, we can reject the null hypothesis only when the observed value of the chi-square statistic is at least 7.815. As the observed value of chi statistic is only 3.28, we cannot reject the null hypothesis. Now, we will move further using F-test. This F-test is used when testing of hypothesis is done for two population variances. Before applying t-test for differences of two population means, one of the requirement is to check the equality of variances of the two populations. This assumption can be checked with the help of F-test for two population variants. For example, an economist may want to test whether the variability in income differ in two populations. A quality controller may want to test whether the quality of the product is changing over time, etc. What are the assumptions? The assumptions for F-test for testing the variances of two populations are: number one, the population from which the samples are drawn must be normally distributed, and the samples must be independent of each other. Now, We move on to block 4, that is forecasting methods, which includes business forecasting, correlation, regression, time series analysis. So we will start with business forecasting. In today's highly dynamic business environment, managers have to forecast the future and design strategies accordingly. The success of business depends mainly on future planning based on the past and present experiences. The experiences may be based on the quantitative and or qualitative factors. Both of these types of information helps managers in business forecasting. Managers use forecasting, the art of science of predicting the future, techniques to take strategic decisions about selling, buying, hiring, etc. every day. The past data are used by managers to make predictions about the future. Now, forecasting is essential in order to make reliable and accurate estimates of what will happen in future in the face of uncertainty. The flowchart of forecast and the decision-making processes is like this. Forecast sets strategies. When strategies are made, the decisions are taken, and a planned performance is made. Monitoring system is over there, and with the decisions and the monitoring system, the actual performance is calculated. Decisions are also get influenced by the additional information obtained by using the forecasting methods. Such information and the perceived accuracy of the forecast may also affect the strategy formulation of an organization. Thus, an organization needs to establish a monitoring system to compare performance of the plan with the actual one. Some of the objectives of forecasting are: number one, creation of plans of action, because it is not possible to evolve a system of business control without an acceptable system of forecasting. Number two, monitoring of the continuing progress of action plans based on forecast. Number three, the forecast provides a warning system of the critical factors to be monitored regularly because they might drastically affect the performance of the plan. Distinction among prediction, projection, and forecasting. Prediction is a future estimate based on extrapolation. Hence, prediction is solely based on past data of the series under investigation. Whereas a projection is a prediction where an extrapolated value of a subject to certain assumptions. And a forecast is an estimate of some future point of time, partly based on past and present data, and partly on subjective estimates arising out of the experience and judgment of the forecaster. So these are the basic the differences between prediction, projection, and forecast. Now, what are the steps in business forecasting? First, to know the causes of change in the past. While attempting to forecast business fluctuations, a clear understanding about the causes responsible for the past changes is must. Number two, to measure the phases of business activity. Having known the cause of occurrence of the fluctuation, certain phases of business activity needs to be computed so as to forecast the changes which are supposed to occur after the current level of activity. Third one is selection and compilation of data. The business barometers form the basis of statistical available for measuring the fluctuation in business activity. And the number fourth is analysis of the data. The data needs to be analyzed in the light of one's understanding of the reasons why changes occur. If it is known that certain factors have resulted in a given change, then these factors are to be computed statistically to draw conclusions about the future. What are the methods of business forecasting? There are two broad, these are classified into two broad categories. Number one is quantitative or objective, and the second one is qualitative or subjective. And they are further divided into different methods. Whereas from the diagram, it is depictable that the forecasting methods are divided into two branches or two categories. One is qualitative and the other one is quantitative. As far as quantitative is concerned, it is divided into two, that is time series and casual. Different methods are there to judge or to calculate what will happen in future. Qualitative forecasting methods. These methods consist of collecting the opinion and judgments of individuals who are expected to have the best knowledge of the current activities or future plans of the organization. And important advantage of qualitative method is that they are easily understood. Another advantage is that they can incorporate subjective experiences as inputs along with objective data. Again, the cost involved in forecasting is quite low. These methods have some limitations also. One serious limitation is the varying perception of people involved in forecasting. As a result, intuitive forecasts are likely to differ from one individual to another, and wide variance is found in forecasts. These methods are suitable when forecasts are to be made for highly technical products which have a limited number of customers. Personal opinion. Here, an individual does some forecast which can be relatively reliable and accurate of the future on the basis of his or her personal judgment without using a formal quantitative model. This approach is usually recommended when the conditions in the past are not likely to hold in the future. Panel consequence consensus. To reduce the prejudice and ignorance that may rise in the individual judgment, it is possible to develop consensus among group of individuals. Such a panel of individuals is encouraged to share information, opinions, and assumptions, if any, to predict future value of some variable under study. Then comes Delphi method. This method is very similar to the panel consensus method. In Delphi method, a group of experts who may be stationed at different locations and who do not interact with each other is constituted. Thus, a questionnaire is sent to each expert to seek his or her opinion about the matter under investigation. A summary is prepared on the basis of the written questionnaire. On the basis of this summary, a few more questions are to be included in the questionnaire, and this modified questionnaire is again sent back to the experts. This process, which generally keeps them informed of each other's forecast, is repeated until the desirable consensus is reached. This is Delphi method. It is an iterative procedure in which revisions are carried out by the experts till the coordinator gets a stable response. This method is very efficient if properly conducted, as it provides a systematic framework of collecting experts' opinion. By virtue of anonymity, statistical analysis and feedback of the results, and provision for the forecast revision, results obtained are free of bias and generally reliable. Then comes market research. The marketing research method is introduced in order to collect data, and accordingly, a well-designed questionnaire is prepared and distributed among the respondents. On the basis of the responses obtained, a summary is prepared, and the survey result is developed. Now we move on to quantitative forecasting methods. These methods can be used under the following situations or conditions. Past information about the variable being forecast is available. Available information can be expressed numerically. A reasonable assumption is that the pattern of the past will continue in future also. Forecasting for medium and short-term decisions. Forecasting for the medium and short-term horizons from 1 to 6 months is commonly employed for production planning, scheduling, and financial planning decisions in an organization. We can classify these methods into 5 categories. First one, subjective of intuitive methods. Number two, based on an averaging of past data, that is moving average and exponential smoothing. Number three, regression models on historical data. Number four, casual or econometric models. And number five is stochastic models, which time series analysis and box Jenkinson models. Subjective of or intuitive methods, these methods rely on the opinion of the concerned people and are quite popular in practice. Top executives, salesmen, distributors, and consumers could all be approached to give an estimate of the future demand of a product. And a judicious aggregation, adjustment of these opinions could be used to arrive at the forecast of future demand. Committees or even a Delphi panel can be constituted for this purpose. However, all small methods suffer from individual bias and subjectivity. It can not be documented and programmed for use on a computer so that no matter whether A or B or C makes the forecast, the result is the same. However, subjective and intuitive methods have their own advantages. Marketing or other functional areas may be the only method available to forecast and to plan future operations. What is exponential smoothing method? Exponential smoothing is another technique used to smooth a time series of its sharp variations. It is a type moving average forecasting technique which consists of a series of exponentially weighted moving averages. The exponential smoothing method weighs data from the previous time period with exponentially decreasing importance in the forecast. This method has a relative advantage over the methods of moving averages. This method focuses upon the most recent data. Second, during forecasting, this method takes into account all the observed values, which, because each smoothing value is based upon the values observed previously. This method is used for forecasting when there is no apparent trend or seasonal variation in the given values of a variable. However, this method is useful mostly for short-term forecasting, like forecasting of sales, inventory, price, etc. So we can develop a formula like this: Ft is equal to Ft minus 1 plus alpha into minus dt minus Ft minus 1. So when we will simplify it, we will get this alpha d1 plus 1 minus alpha into Ft minus 1, where alpha is the smoothing constant that lies between 0 and 1, but generally chosen value lies between 0.01 and 0.30. A higher value of the places more emphasis on recent data. To initiate smoothing, a starting value Ft is needed, which is generally taken as the first or some average demand value available. Another method often used in time series analysis is to identify the following four major components in a time series. Number one, secular trend, that is long-term growth in market. Number two, cyclic fluctuations, that is due to business cycles. Third one is seasonal variation, that is woolens when demand is seasonal. And number fourth is random or irregular variations. Now we move on to unit 14, that is correlation. What is meant by correlation? Correlation refers to the association between variables. When an association exists between two variables, it means that the average value of one variable changes as there is a change in the value of the other variable. A correlation is the simplest type of association. When a correlation is weak, it means that the average value of one variable changes only slightly, that is, occasionally, in response to the change in the other variable. If there is no association, it means that there is no change in the value of one variable in response to the change in the other variable. In some cases, a correlation will be positive or it may be negative. A positive correlation means that as one variable increases, the other variable also increases. That is, height of a child and the age of the child. They have a positive relation. On the other hand, negative relation implies that as one variable increases, the other variable decreases. For example, value of the car and age of the car. The depreciation is there. What are the causation of correlation? The correlation between two variables measures the strength of relationship between them, but it does not indicate the cause and effect relationship between the two variables. Correlation measures covariation, not causation. Causation means change in one variable affect causes the changes in the other variable. In other words, just because two events or things occur together does not imply that one is the cause of the other. Correlation may be positive and negative, and it can be. Second type is linear and non-linear correlation. If two variable changes in the same direction, that is, if one variable increases, then the other also increases, or one decreases, the other also decreases, then it is a positive correlation. For example, advertising and sales. And some other examples of positive correlations are height and weight, household income and expenditure, price and supply of commodities, amount of rainfall and yields of crop. The second one is if two variables change in the opposite direction, if one increases and the other decreases and vice versa, then the correlation is negative correlation. For example, TV, registrations and cinema attendance. In some of the other examples of negative correlation are volume and pressure of perfect gas, current and resistance, keeping the voltage constant, price and demand for goods. These are the examples of negative correlation. Then comes linear and non-linear correlation. The nature of the graph gives us the idea of the linear type of correlation between the two variables. If the graph is a straight line, the correlation is called linear correlation. And if graph is not a straight line, the correlation is non-linear or curvilinear. In general, two variables x and y are said to be linearly related if there exists a relationship of the form y is equal to a plus bx, where a and b are two other real numbers. There is nothing noting but a straight line when plotted on the graph sheet with different values of x and y for constant values of a and b. What is degree of correlation? Through the coefficient of correlation, we can measure the degree of extent of the correlation between the two variables. One of the bases of coefficient of correlation, we can also determine whether the correlation is positive or negative, and also its degree or extent. Perfect correlation, if two variables change in same direction and in same proportion, the correlation between the two is a perfect positive one. According to Carl Pearson, the coefficient of correlation in this case is +1. And on the other hand, if the variable changes in the opposite direction and in the same proportion, the correlation is perfect negative and its value is -1. Absence of correlation, if the two series of the two variables exhibit no relation between them or change in one variable does not lead to a change in other variable, then we can firmly say that there is no correlation or abstract correlation between the two variables. There, in that case, coefficient of correlation will be 0. Thus, we can say that correlation may be positive, negative, or 0. but it has limits, and the limits are plus minus 1. So, mathematically, we can say that the value of R lies between minus 1 and plus 1. If plus and minus 1 signs are used for positive linear correlation and negative linear correlation, respectively. Degree and type of correlations. This figure depicts what we have discussed till now. Absence of correlation, 0. In both cases, perfect correlation is plus 1 and minus 1 in the negative one. High degree of correlation is from plus 0.75 to plus 1. And high degree of negative correlation is from minus 0.75 to minus 1. Moderate degree plus 0.25 to plus 75. And similarly for negative. And for low degree, it is from 0 to 0.25 and to 0 to minus 2. Minus 0.25. Note that R is a dimensionless quantity and this does not depend on the unit employed. With this, we conclude today's session. We will be meeting tomorrow and we will continue with correlation as well as some numericals on the subject.